Uh, Greetings, everybody. This is Vinay from the Thai Bangalore team, and we are glad to have Wasim Sheikh from Analog Devices. This session is brought to you by Mauser Electronics, and we're also streaming it live on YouTube and multiple distribution channels. So feel free to share your questions, queries over there, and we'll put it across to the speaker. Over to you, Wasim.
Thank you so much. Yeah. So, good evening, everyone. I hope I'm audible and you do see my slides now currently on the channel. So,
Yes.
today's talk is going to be about precision converters. What new innovation trends are we kind of incorporating in our data converters in order to make sure that your life is easy. You're easy to integrate. You're easy to design in. You're easy to do a whole lot of things quickly. As we see today that there are a lot of cycles around getting the product right. So we want to ensure that you do have all the means in order to make sure that you are able to get it right the first time, right? So as mentioned, my name is Wasim. I'm the product applications manager for precision controller converters team in Analog Devices. What I mean by precision converters is that we make all this kind of 24-bit, sigma delta ADCs and other converters like SAS and all, which are like 18-bit, 20-bit, or it could be DACs, digital to analog converters, which are like 20-bit also, right? So with this, let's get started. So as I said, I'm a part of Analog Devices. We recently integrated Maxim, and some years back we have the linear company as well integrated within us. So we are all part of Analog Devices, right? So, right. Slide. All right. So today's agenda, firstly, I'm just going to touch upon what is converters per se, right? Because I don't want you all to be confused with what type of products I'm talking about, right? Then the next item on agenda are the innovation trends at ADI that we are using in order to make sure that our products have much higher value. Things like low power, how we are doing in terms of low power, what low power ADCs we are designing, and what are the applications. Then with regards to integration, meaning putting more and more amount of ICs onto one single chip or one single small package, right? With regards to that, what are the new parts that we're talking about? Then with regards to architecture, right? So how architecturally we are trying to solve the customer's problem by getting in new innovations in that. That is something that I would talk next. Lastly, I would like to talk about the industrial function safety. This is become apparently a kind of a new requirement for a lot of industrial applications. Like everyone wants functional safety, everyone wants to have clear of their liabilities, around this. Lastly, I'll touch up upon some tools, some of the interesting ones, which can really ease out your overall design journey. It can help you to select the correct parts. It can help you to select the correct circuits, those type of things, right? All right. So with this, let's get started with what are converters, right? So what are converters? We all know that temperature sensor or say JK type thermocouples or maybe something like a MEM sensor or something. They would give a signal which is kind of continuous in time, right? And it is of analog nature. So all your real world sensors, they give out a signal which is very much in continuous in time. So something like this, right? And in order for our controllers or microcontrollers or microprocessors to understand these signals, we need some process in order to digitize them, in order to convert it into ones and zeros to binary form, so that our machine is able to process that, act on it, and then decide upon that, right? So let's say this example over here I show you, right? So let's say there's a furnace, right? And it is kind of trying to heat a particular element. And let's say that above 85 degrees, the furnace should stop, right? This is the primary function. So what happens is maybe you have a thermocouple, right, that keeps reading the temperature. It gives out electrical signal, which is over here. I hope you all guys see my cursor. And that signal kind of goes to something called as an analog to digital converter, right, which will convert this continuous time signal into a digital signal, as you see over here, right, on the right side. And then this signal is then fed to a DSP or a microcontroller or something, and then based on the value, it would take a decision. So let's say, for example, the temperature has exceeded 85 degrees, and it is the DSP will make out this, and then he will try to control a DAC or a digital to analog converter to send some kind of an excitation signal to switch off the furnace, right? That's what the intended purpose is. So going from left to right is the analog to digital conversion, and going from right to left is a digital to analog conversion, right? Just to make sure that both the kind of planes do understand each other, right? Just an example over here. So an ADC sampled and quantized waveform would look something like this, right? It would have these snapshots at the sampling frequency, and this all will correspond to some kind of a digital value. And your DAC or digital to analog waveform would be something similar to this steps as you see over here, which will try to come very close to the actual signal. But these are all covered under the specifications. So as long as this is okay, you're fine. So for this talk, I'm just going to focus upon some of the new stuff in analog to digital converters, right? How we are doing with regards to the four aspects that I mentioned about it earlier. So with this bare understanding, with this base understanding, now let's move and let's discuss about analog to digital converters. Right. So well, the first item I want to speak about is low power. Right. Power, we know it's very crucial for us. It's very we want to have everything very small, very low power, so that your edge computation or at the end computation is eased up, is simplified, right, and you get a lot of intelligence built onto the end nodes, right. So that is the first part that I'm going to discuss about, which is basically AD4130. It's essentially a very low power analog to digital converter with about 4 or 8 channels, right? It is very much used in applications like smart transmitters. So if you have pressure or temperature transmitter, which works on something like 4 to 20 milliampere loop, all those for those applications that can be used for wireless battery. Right, this particular ADC with a coin cell can go for 5 years, right? So you could use it a lot for your wireless type of applications. Portable instrumentation, very very crucial now. We see all this kind of with COVID, the temperature sensors and all, which are very very much portable. Then pressure measurement, then healthcare wearables, very crucial. Right, we are doing so many type of things. We are doing stress, we are doing the heart rate, and I think there's a lot of research going in terms of a non-invasive sugar measurement or blood pressure measurement. How do we get it on a very small chip into your watch in order to ensure that we have a good level of diagnosis 24/7 always there for you. Any type of portable equipments, and even environmental monitoring, which is very so crucial. You can think about air quality sensors or CO based sensors that are hung up like GPS tags onto your cars or onto anything that is moving, that can give you a good image of how is the environment in overall doing, right? Those type of things, right? This particular IC that I'm going to talk about, a low power one, is a very very small package, so it can be put onto wearables and stuff like that. And then it has got of very good features like FIFO and duty cycling, which would kind of take away a lot of your load from your microcontroller or your microprocessor, right? So this new part, right, like I mentioned, it is used for a lot of applications on pressure, voltage, current, and thermistors, right? It is a very very low current ADC, with a coin cell battery. It could go for more than 5 years or so, right? Heavily integrated. It has got programmable gain amplifier. It has got excitation current, but I'll just talk about it in an application diagram. It has got all the reference, the clock, everything integrated, a lot of diagnostics, everything. Along with this, there are two niche things that we have integrated. One is called as a smart sequencer. What a smart sequencer does is basically, if you have a lot of sensors that are connected or to different ones, and say if you for power sake you don't want to scan all of them and maybe scan select ones, or maybe have some kind of a altogether different sequence. Say I want to channel 0, 8, 7, any sequence, right? All those things can be kind of programmed into it, and then what will happen is it will go and then it will read those values and give it back to you, whatever you need, right? The other niche feature that is added is FIFO. So your microcontroller doesn't need to keep going and interrogating the ADC always for give me the data or get me the data. He will have a kind of a FIFO that he will keep filling internally, and whenever he is full, he can raise an interrupt to the micro so that the micro can do a lot of better things that he wants to do. And whenever the ADC kind of goes and wakes him up, he can go and he can read the values. You can set different things. You can set alarms. You can set a lot of items with this FIFO internally to this. So this we can use it over a standard SPI interface. This can go up to all the way from 1.7 to 3.6. What this means is that you could have lithium-ion battery packs or coin cells and all those things to operate this particular ADC. And remember, this is all 24-bit precision we are talking about, right? So this becomes very handy in a lot of temperature and pressure type of applications. Right. So let's think about this, like where and how it will get used, right? So here, what I'm putting up is kind of an RTD temperature sensor diagram over here, right? So overall, if you look at it, towards the right, this is a digital board. This is a kind of an Arduino header that you can find in any ST micro boards or many things, right? And that can be directly interfaced to this ADC. The ADC just needs a kind of a 3.3 volt power, and all the other things it will kind of generate it internally and use it internally. Now, at the application side or the sensor side, you just have this block over here. It's called as the RTD, right? And then it has a reference for kind of compensations of cold junction and stuff like that, right? So here, if you see, right, you have an RTD and then you have excitation currents that you can set to whatever value you want, right? And you can excite the particular channel or a selected channel with that excitation current, and it can go and you can read back those values. Now, as I mentioned about a smart sequencer, right? So you could do any sequencing. Say you excite channel 0, read it back, and then maybe you can just go to channel 7 or channel 9 or whatever, or vice versa, whatever. Right, and you can go, you can excite and read back and keep reading these values. So this is one of the one of the application diagrams that is very much used in kind of this industry smart transmitters, temperature transmitters, and stuff like that. Right. This part also has a good set of diagnostics, so you could kind of always diagnose that if your particular soldering is fine or not, if anything has broken on these input channels, or if anything has kind of gone bad anywhere, right? It has also got memory and CRC checks in order to make sure that your ADC is always working fine, he's always alive, those type of things. So a good amount of diagnostics are built in order to make sure that this guy is able to completely diagnose by itself and make sure all the features are working fine. Right. I have a separate time for questions at the end, so we'll keep moving, and then at the end we can have all the questions. Yeah. Right. The next area that we are doing is on integration, so which we call them as micro modules. So this is about how do we integrate dies onto one single package, and what are the offerings in those terms, right? Now, the first, so this is the whole idea, right? So basically, whenever you lay down the ADC, the driver, the in-amp, the discretes, it looks pretty big, right? On a PCB, it's like 15 to 50 cross mm. This is an example over here. What we are offering is we are offering a single package that holds all these resistors, capacitors, all these three ICs you can see over here in a kind of a 6 mm cross 12 mm package. And if you kind of just look at it over here with a peeled down version, you could see all these three dies which are there, and then you can see all these discrete components over here. Correct. So this part over here, whatever I'm showing you, it kind of holds an instrumentation amplifier over here. Then it has a driver, and then it has a a fourth order anti-alias filter. It also has the ADC, a 24-bit kind of sigma delta ADC, right? And power regulators, discrete supplies, everything. Now, along with the space reduction that I'm talking about over here, right? The other important thing is about the design liability, right? What I mean by that, so let's say that you choose an ADC, you choose a driver, you choose an in-amp, you lay it out like this kind of a board over here, right? You have to always worry about how this circuit would look like. How do you make sure that it performs correctly? How do you make sure that it's optimized rightly for your right set of application? How do you ensure that all these components are stocked well whenever you need them? They're all available for you. All those items you have to make sure, right? But here what is happening is, when we have integrated all of them inside this particular package, we assure you that whatever the performance will be there, it's all mentioned on a data sheet, right? So the entire liability is kind of we have with us. We are saying that, okay, 107 dB of dynamic range, right? So we have ensured that all this circuit is as per that and internally over here. So all you have to do is just to wire a sensor, and you can assure that everything, all the specifications met are there available on a data sheet, and you don't have to struggle with any of the optimizations, any of your designs and all those aspects, right? More importantly, since all of them are integrated, your BOM management is also simplified. So all you have to do is just make sure that you have this IC available. That's all. Everything is just internal. So if you look at it from a application schematic, right? So this application schematic over here is a kind of a condition-based monitoring solution, right? What you have to do is you have to just connect your MEMS sensor or your IEP or piezo type electric sensor just to the input, right? This complete block over here you see is the entire ADC, right? So you have to just put up the reference, just connect the sensors directly, throw in some decoupling capacitors, right? And you're just good to go. You can just directly connect it with your, with your microcontroller, with your, FPGA or whatever, right? So if you look at it, right, overall, say when you take this IC, all you have to worry about is maybe, just put these decoupling capacitors, and the entire other stuff is all internal. You don't have to struggle with any of the aspects. So wherever you have a smaller size, wherever you have a lot of isolation requirements, right, channel to channel isolation and stuff like that, you can always go for the single channel solution that I'm showing you over here. In line with this, there are a lot of other micro modules as well, which has basically SAR kind of architectures integrated. So I can share the link later on, on the channel comments, in order for you to kind of look at it. But this is the whole idea. We are integrating all of them together so that your problems are solved. You don't have to struggle with the design, nothing, right? Right. So with this, I will go on to the next item is basically how we are doing in terms of designing new architectures, in our data converters or in our ADCs. So the first the one of the items or one of the applications I've just picked up is the continuous time sigma delta architecture, which is kind of a variant of the discrete time sigma delta architecture. So what do I mean by that? So all ADCs, right, be it successive approximation type or be it discrete time sigma deltas, whatever you see the conventional ones on in the market, they all have a kind of a switched capacitor at the input, right? So what this does is basically it will take the sampling shots, right? So it will just sample for a moment, it will close the switch and will open the switch, right? It will show that value, and then that value is kind of taken up, kind of digitized and filtered and given to your microcontroller or whatever, right? Now what is happening is, because of the switch capacitor, whenever we open and close the switch, right, there is a surge in current, right, which happens at the capacitor. And because of this surge in current, there is a kind of a kickback that is given to your sensor, is given to your whatever front end IC or amplifier or whatever. Now, because of this, right, we have to always make sure that we have a kind of high bandwidth kind of an amplifier which is driving this input to ensure that because of the switch cap, we don't have any kind of distortion or any kind of ringing or anything like that, right? Now, the other problem that it also induces is called as aliasing. Because of the switch capacitor input, we tend to alias back a kind of high frequency signal back to a low frequency signal, right? Which is the other problem, and that is why we use a kind of a analog input filter to ensure that we don't have any high frequency input noise over here, right? Now, the modified architecture, the new architecture that we got into a few parts which got released last year is the continuous time sigma delta ADC. What our design guys have done basically is they've moved this piece over here, the switch capacitor input much later beyond the quantizer, right? So it looks something like this. So the advantage of this is basically that whenever we are looking at the input of the ADC, we always see a resistive load, right? And what this means is that we no longer need a driver or an amplifier to drive the switch capacitor input, correct? So that makes that tells us that there is no sample and hold circuit in the front, right? And we don't need a high bandwidth driver over here. The other important thing is that since this switch cap is moved inside the loop, sigma delta loop, any type of aliasing, right, will be cancelled out. So this particular loop, it has a frequency response such that all the tones around the sampling frequency are rejected inherently by this particular architecture. So what does this mean is that we no longer need the analog input filter, right? So with these two kind of innovations, what happens is that our circuit is basically alias free, meaning we don't have any aliasing, and it's resistive inputs. So we don't have any kind of switch capacitor that we have to drive. Now, over here on the top side, I'm just ignore the crosses for this sometime. A conventional signal chain with a SAR ADC or with a sigma delta ADC, you will have a driver or an amplifier to drive the switch capacitor input. You will have these filtering components that do the low pass filtering. Similarly, you'll also have a similar problem on the reference as well, right? For which you need a reference buffer and use some filtering components and stuff like that, right? Now, with this continuous time sigma delta architecture, what is happening is all these components are removed, right? So what happens with this is that your design is very simple, right? It is just the enamp and the ADC. There are no discrete components, no drivers, nothing like that in between. So it is just a mere interconnection of two integrated circuits, two chips just next to each other. So what this means is that your design is very simplified, right? You can just connect two ICs together directly. There are a lot of savings with regards to area. We are estimating about 70% of area savings when we lay it down on a PCB, right? The other aspect is also that your BOM management is eased out because you no longer have to worry about procurement of all these components. Your cost is saved because the number of components are less, and you also have an increased reliability because the number of components is less. The failure rates that plane because of these components is totally removed. What does that mean is that your mean time between failure number is very high. So your product can be more reliable, it can have more life, right? So when we compare a kind of a quad channel solution with regards to the traditional discrete time or SAR architecture, you will need so many amount of resistors, 20 capacitors, 40 resistors, some 4 or 5 ICs, right? These type of components. But when we take the continuous time, this new architecture, there's nothing, no resistors, no capacitors, all those things in the signal chain, right? So this means that our bill of material is reduced, its management is reduced, the cost is reduced, as well as the space is reduced. So let's imagine a kind of a sonar application, right? And you have, say, 256 number of channels, right? So 256 number of channels feeding into this ADC, and you can imagine the amount of savings that is there. So here, I'm talking about only 40 resistors for 4 channels. So maybe for 256 channels or 512 channels, this number is going to go way, way, way beyond. And all type of sonar applications, you want to make sure that once you design it, it is very reliable, right? And it is also has a very long life, because the problem that happens is that such type of products, they take like maybe 3-4 years to design. So the expected life expectancy out of it would be like 20 years, 30 years, or maybe 50 years, right? You don't want to keep on changing them very frequently. So for such type of applications, this type of architecture is very, very much favored, right? So any kind of equipment which you want to have a longer life, which you want to have it in a tight space, in a dense environment, you would be going for this particular type of architecture and particular type of ADC. Right. So with this, I come to the next topic, which is functional safety. Right. It's very crucial with regards to the industry 4.0, or even for a lot of applications, right? Um, be it be it anything that involves human life, right? Uh, Classic examples would be aeroplane systems, or maybe a railway signaling system, right? So how do we make sure that whenever the signalman actuates your red, green, or yellow light, right? It's always red. How do you ensure that electronics will always set it to red? How will you ensure that it always sets to green or orange or whatever? And you can imagine how fatal it would be if the signals are not correct, right? So you would go for if instead of red, green comes, you can just imagine the amount of life loss that would be there. So those type of things kind of get covered in functional safety, which is basically to ensure that you don't have any kind of random failures, right? Be it due to temperature, corrosion. So let's say in your sensor, if there is a capacitor and that has got corroded due to environment or any such factor, right? And if it is not working correctly, right? So how do you make sure that firstly it works? If it doesn't work, at least it says, or it tells your signalman that, hey, look, I'm not well, okay, come and please attend me or repair me or whatever. Okay, so this is all aspect about the functional safety, right? So back in about maybe 30 years time, 40 years time earlier, right, there was an equipment that used to make all these things kind of for this chemotherapy and stuff, radiations, right? Now what happens is that such equipment back then, right, it was not functionally safe. And what the outcome was that there were massive overdoses of radiation. Okay, because of that, there was a lot of accidents, like 6 accidents mentioned over here between 1985 to 1987. And due to the loss of functional safety, there were a lot of problems, and a lot of lives were lost because of this not being functionally safe. So be it medical, automotive, anything, right? The functional safety, is very, very, very important, right? You have to make sure that your equipment is kind of free, okay, from any kind of random failures. Now, although when I say this, it's not completely 100% possible, but we have to make sure that at least it is probability is very, very low of that failing or with that, right? So this is why functional safety is important. Now it is difficult. Functional safety, why it's difficult? Okay, when I purchase any resistors, capacitors from a market, I just put it up. Now how can I say that this is going to be alive for next 10 years or 15 years or 20 years? Now, for this reason, you have kind of a lot of these, functionally safe design engineers who would kind of assess a particular signal, and they will tell that, okay, hey, look, you need to make sure you have this XYZ stuff along with these components in order to ensure that, your random failures are, very, very low. So this entire subject, even definition of whatever area you want to be functionally safe, all these things is a bit complex and needs a kind of a good amount of expertise in order to make sure that your design is always certified. Then this also needs to be kind of it's expensive, because what happens is let's say your car has a brake, your car has a brake, sorry, obviously. Yeah. So how do you make sure that the brake always works on time? So a guy or a common guy would say, okay, let me put two of them. So at least one of them doesn't work. I'll put the other one. So this is one way of doing function safety, wherein you kind of add redundancy to your design in order to make sure, okay, one doesn't work, the other one will always work. But then what this happens is that your overall component cost increases. You need to have two brakes and size increases, all those things, right? Now, the other way to do function safety, so hence function safety is expensive, it needs space and all these things, right? The other way to do it is you may have a diagnostic around the brake. So let's say the brake is not working due to some reason, right? So maybe when the car starts up or boots up, right, he will kind of assure that the brake is okay and he'll tell you, yes, brake is fine, you can go ahead and you can use it. Okay, so that way, you can add diagnostic, but all these things, it needs space, power, everything, and hence it is kind of expensive and needs space. So what we have done in analog devices is that we have come up with functionally safe ICs, which are like approved to a particular safety level, by the certifying agencies. One of them being the TOV, which is in Germany, Mainland. Right now, when I'm saying this is like a kind of very much used. This is a DAC, digital to analog converter, that is used for this current output modules or current output channels in industries. Now, so how is it achieving functional safety? Essentially, it has got super diagnostics internally, right? So let's say you want to excite a particular output, right? So what happens is inside the very IC, right, you have something that will read back this whatever you're exciting. So let's say you have a I out over here and you set X amount of current, right? Now what happens is it has an internal ADC that will read back, okay, hey, you have set 1 milliampere, you are also reading back 1 milliampere. So that way, all these diagnostics are kind of integrated in order to make sure that your design works very well. Now, let's say you excite it and it's not correct, right? So it also has all these mechanisms to make sure that the user or the microcontroller is alerted that, okay, yes, I'm not fine, and come and look at me or correct me or whatever. So there are independent kind of monitoring ADCs that would kind of make sure that all the electronics inside it is kind of working correctly. We have engaged with TUV, the certifying agencies, and make sure that this part can be used for SIL2 type of designs, right? So all you have to do is you have to just take these parts and use it in your designs, and we provide a set of documentation and stuff like that that you could use it for your end product certification. So you don't have to worry about any documentation pertaining to this particular ADC. That really eases up a lot of your overall design process. On similar lines, we would be having further DACs or further ADCs that would have the functional safety integrated and will be approved by the agency in order to use it. All right, so I think I've spoken about all the 4 aspects that we are working on. I think the last item that I just wanted to show you about is the tools. These are all kind of simulation tools, and these are all kind of tools that you could use in order to kind of design your schematic or simulate it, see what part will be the best for your kind of application, right? Let's say, for example, over here, I show you about 8 kind of different tools that are there over here. We call them as ADI Precision Studio, right? And then these are kind of individual items in that, wherein you can go ahead and use it. So let's say, you want to design a kind of a filter, with X amount of specifications, we can always go there to the analog filter tool and design that. Maybe I'll just stop sharing for just some seconds and I'll just show you directly on the web how it looks like. Give me a minute. All right, so I hope you see my screen now. It is a ADI PC Studio web page here.
Yes.
Thank you. Yeah, so it has these different tools, and you could just go to tools.analog.com Precision Studio, and you can all these tools will show up. So let's say ADC driver. Okay, let's start with this. So you basically click this, right? And what it will throw up is it will throw up a kind of ADC selections that you want. So let's say you have thought that maybe AD 7768 is the best ADC for your particular type of application. Okay, so now the next kind of logical question for you is that, okay, what is the front end driver? What is the front end buffer that I can choose, right? So when I chose directly 7768-1, it showed me the recommended one. Okay, that will pair up with the 7768-1, right? Now, with this ADC, it will throw you all the components that you have to put in order to integrate. It will show you, how is the noise and the distortion of the complete signal chain, right from the input to the output, including the ADC noise. So say, it will show the complete noise. It will show that total system noise is how much, and what is your driver noise contribution. Okay, driver noise contribution means noise contribution because of this 4945, right? It will show you, your input settling graphs. How is your input settling, right, with whatever the RC is there. And it will also show you the next steps on to downloading LT-Spice simulation or the summary PDF and stuff like that. You can, let's say you're retrofitting your design, and let's say you have a totally different front-end driver. So you can select from this set of drivers over here, whatever is there, which is recommended for the part, right? We also have several others that you could use. These are not recommended, but maybe, with slight modifications, you can do it. So let's say I've selected this 804075-2, right? And with this, it will show you how the schematic should look like, and the problem with that, right? So he'll say that, okay, hey, look, your RC filter bandwidth is not right, correct? So what you have to make sure is that either you have to reduce your sampling frequency over here, or change the driver, right? One out of the two. So maybe you can go for a slightly slower speed, slightly slower, and with this, everything, not all the red marks are gone. Right, and with that you can, so basically you can just play around and you can design your entire circuit with whatever kind of recommendation is there. Then you can also change the sampling speed of this ADC and to whatever you want, and you can choose. You can also choose what type of filtering you want to use, what type of reference you want to use, then even whatever gain you want, what configuration you want, inverting, non-inverting, follower, all those type of things you can play around. You can even look at how your output would look like if your input is differential, single-ended, with whatever frequency, right? All those type of things. You can even change the RNC values over here, play around with it, and see how your circuit is behaving basically. So this is very nice tool over here. It can give you a good indication of what front ends to use, because a lot of times a lot of guys are very confused to figure out what should be going in front of the ADC, right? So this is called as the ADC driver tool, right? Maybe I can go on to the next one. Sorry, it's give me a second. Just go back. Okay, back to the first page. Not sure why this was not going back. Anyways, yeah. So this is the ADC driver tool. Then you also have things like say photodiode, right? So any type of your SpO2 type of measurement, or blood analysis, or anything like that, right? All these things would this would kind of help you design in your front end. What should be the transimpedance amplifier, what part it should be, all those type of things, right? You can even, if you have a particular photodiode in your mind, right, that okay, I want to use this for my previous design, you have all these kind of photodiodes available over here. You could choose a particular one, right, and then you can enter all these parameters as to whatever, and then maybe choose your this. So it will show the photodiode model. It will model it completely. It will also tell you that how your response is. You could look at the circuit design. You can see the kind of frequency response, how the spectral noise is, how the noise gain is, how the SNR is. All these type of things you can see with the photodiode current circuit design. So this will help you to really choose your kind of front end transimpedance amplifier, as we call it, current to voltage converter, those type of things. And again, the next steps would be to kind of maybe the bill of materials, all the individual calculations, and even some spice files in order for your own work ahead, right? Then the other, although there are many of them, maybe the filter one is, maybe that would be helpful. I can just quickly show you that, right? So here you could kind of choose whatever you want, say the anti-alias filter that I was talking about. So let's say you want to have a low pass, you want to have a 3 dB cutoff, say maybe at 10 kilohertz, you want stop band, whatever, and it would give you a kind of the response, right? It would give you a magnitude response, it will give you a kind of a phase response, right? Group delay, whatever, right? All the things, it can give you, it can help you choose the what should be the components, what should be the ADCs, right? How much is going to be the noise that is going to be incurred, all those type of things. You can play around by changing these components as well. You can click over here and change the ADC. You can choose whatever level of optimization you want, low noise, voltage range, low power, anything, right? And you could also choose whatever you want, right? And similarly, you can go for band pass, high pass. You could change the stop band. Let's say maybe make it say 20K or whatever, uh, right? And you could kind of do that, right? So it will give you kind of a steep filter. It will give you kind of a higher phase delay. So here you could kind of just play around with it, and you can choose whatever is needed kind of for your design, right? The one last tool I just wanted to show you was on Inamp. Inamp, we are always while deciding, whenever we choose a sensor which has some kind of a common mode biasing or anything like that, right? We are always worried about, is my input in line, or will it get accepted by the instrumentation amplifier? Then what is the amount of gain I can have, with which, even the output is fine, I don't exceed the output, all those type of things, right? So you could set your common mode voltage here. You can set the gain. You could choose whatever instrumentation amplifier you want. You can have whatever all configurations, single-ended input, or kind of differential input, or whatever, right? All those type of things. You can program the supply gain. You can choose from a wide set of instrumentation amplifiers that is available, right? All those type of things you could do here, right? So okay, sorry, here, yeah. So it will throw you all these options. It has even the linear tech paths integrated inside this tool. All those type of things you can do, and then again, it will show you the diamond plot, right, which kind of tells you what area you should be in order to ensure your circuit is fine. Basically, the V out versus the common mode voltage, right? How much it should be, and then everything. I mean, recommended paths, how the circuit should look like, everything it will show, right? Then lastly is the virtual eval that we have started. So what I mean by virtual eval is that every time to evaluate a particular ADC or a particular IC, right? We always order the evaluation board. We always, connect it, hook it up to your PC, check for the performance, right? Here, what we have done is basically, uh, we have rolled it everything into something called as virtual eval, right? What this means is that you could put different kind of configurations, you could put different type of inputs, you can choose different type of filters, all those type of things. You can choose the sampling speed, reference voltage, everything, and you can just hit run, and then what will happen is that it would compute, all the frequency response, right? How the frequency response will look like for this particular setting, the step response, how it will change with regards to the time, the timing piece, how should be your SPI signals, what timing they should follow, all those type of things it will show you the noise histogram, everything, right? So this really eases out your whole evaluation life, and you could just do this everything online, right? So you no longer need to really order a kind of evaluation board and play around with it. And now everything is available on your laptop or your desktop itself. right? Maybe you can spend more amount of time, maybe you're ordering some kind of a reference designs and all, and then directly integrate it with your end system, right? So these are all type of tools I would really encourage to kind of go ahead and try this out whenever you're choosing any things, right? There are a couple of more over there, like BDS and the digital synthesizer and the noise tool and the DAC tool, all these things. So this would certainly ease up your journey. Right. So this I come to the end of my talk, and I'm now open up for any questions.
Yeah. Suman, any questions we have?
No, Vinay, I didn't got any this.
Yeah. So there's one I noticed online. It's around trying to make sense of it. It's in the healthcare space, around ultrasound imaging systems, and the kind of sensors that they use in the healthcare.
Right.
Would you like to throw some light on what are the use cases in the healthcare domain? Because you've shared quite a bit. Any specific customer use cases?
Right. So we could talk about the maybe the ultrasound, right? The ultrasound diagnosis, right? Be it for pregnancy, be it for any kind of other things. Now, these things are all, it needs multiple amount of channels, right? It needs different type of angles to look at it, and then it would just kind of correlate, and it will show you what image you are really looking at, right? So the part that I spoke about, right? Let me just go back here.
I see Kapil has also raised his hand. Kapil, after this.
So this one over here, the ADAQ7768, right? The micro module, right? This one. Now, this one has all the things integrated, and as I mentioned, it has a lot of channel-to-channel isolation and stuff. Here, you could put any of your ultrasound sensors directly to this guy. Now, this guy can take up anywhere up to 200 kilohertz of bandwidth, and normally your ultrasound sensors or excitation sources are all around 100 kilohertz range in order to make sure that the resolution and even the range is nice, right? So with that regard, this particular ADC is a lot of demand with regards to the bandwidth and with regards to the precision. So even any small signal that is there, the ADC would not really lose it, and it would try to resolve it and show you the data. So this is one of the things that is going a lot in your healthcare type of applications. The other important aspect over here is also that this part is low power. What I mean by this, where I'm coming to, is that whenever you have low power, you can always use some kind of a linear regulators. Now, why linear regulators and why not switching regulators? Switching regulators will have some kind of a switching. So those type of noise could also get appended to the signal, and it can throw you a completely different picture. So a lot of customers, what they want is they want to make sure that the power is low. We use, linear type of regulators to ensure that we have a very low switching noise, right? So this type of particular parts are very, very much useful in such application areas.
Great. So we have a question from online. He raised his hand, but I don't see him. And there are other use cases also where these learnings can be adopted, the entrepreneurial use cases.
Yeah.
Great. So what we'll do is we will source the questions, queries, and we will, through Mauser Electronics, we'll pass them across to you.
Yeah.
And in case of any further interactions, engagements, we'll be happy to do it. We also have it on YouTube live. So many of them will be watching it virtually as well.
Yeah, that would be great. Yeah, and I'm kind of welcome to all the queries, right? And I hope I do resolve them very nicely. Okay, so yeah.
Sure. Suman, if everything is fine, we could, gather the inputs and queries for Wasim and have them answered.
Yeah, sure. We will gather the questions and we'll share it with you, Wasim. And with that, I would like to thanks all the attending and special thanks to Wasim.
Yeah.
Vinay.
Yeah, great, fantastic. Thank you, Wasim, and thank you all. We will share more details and we'll stay connected.
Sure. Thanks a lot.
Yeah.